Good morning, everyone. In this video, we are going to cover section 4.4 and 4.5. Based on the syllabus, we're supposed to cover 4.4 on March 24th, Tuesday, and section 4.5 on March 26th, Thursday. First, let's do some review. Let's say we have a polynomial function p of x, a sub n minus 1, and so on, a sub 3, a sub 2, a sub 1, a sub 0. Those are real coefficients in this polynomial function. X is the only variable. A sub n here is non-zero. A sub n is the leading coefficient of this polynomial function. N is the biggest exponent on the shoulder of variable x, so we define the degree of the polynomial function as n. The degree of the function is n. Let's say we have a constant k. K is a constant. So if we have p of k equals 0, then we say k is a 0 of polynomial function p of x. We could also say k is a solution of the polynomial equation p of x equals 0. We also can say x minus k is a factor of a polynomial function p of x. If k is real number, then k sub 0 is a x-intercept of the function f of x. Okay, and all of them actually are equivalent. We talked about this before. We can label this number 1, number 2, number 3, number 4, number 5. One more, number 6. If we divide p of x by x minus k, then the remainder, which is p of k, we talked about this theorem before, must be 0. Okay, all those 6 statements are equivalent. They are all equivalent. Only in number 5, we require k is a real number. Okay, we require in number 5 k is a real number. In other statements, k doesn't have to be real number. If k is not a real number, is a non-real complex, then the polynomial function does not have a x-intercept at k, 0. So those are very important concepts from previous sections of this chapter. Let's see section 4.4. The title of this section is the fundamental theorems of algebra. In this section, we are going to learn a few important theorems, and then we're going to look at 3 examples. And I recommend, as usual, repeat those examples. Let's look at those theorems. The first theorem, the fundamental theorem of algebra. Let's read the content of this theorem. If p of x is a polynomial function with a degree n, n is at least 1, of course, at least a linear polynomial, right? Then p of x has at least 1 0. The 0 may be a non-real complex number. We actually had a different version of the fundamental theorem of algebra. And I remember I typed them out, the content of the theorem in the class. It told us if the polynomial function p of x has degree n, all the coefficients of the polynomial are real numbers, then the polynomial must has n zeros. The n zeros do not have to be distinct. Maybe some of them are identical, and they don't have to be all real numbers either. It could be a non-real complex number. So I think we'd better use another version of the fundamental theorem of algebra. I can repeat that again. If we have a polynomial with coefficient real numbers, and the degree of the polynomial is n, then the function must has exactly n zeros. We just covered or recalled how do we define zero, right? And those zeros, those n zeros, do not have to be distinct. And those zeros, those n zeros, do not have to be real numbers. Okay? Yeah. So the linear factors theorem actually can be seen as a corollary of the fundamental theorem of algebra. Let's see the content here. We have a polynomial p of x. Leading coefficient is non-zero, guaranteeing that the polynomial function has degree n. All those coefficients are real numbers. Then we are able to factor the polynomial function p of x as the product of n linear polynomials. And those n linear polynomials are all in the form x minus a constant. You can look at this this expression. P of x can be written as a sub n. A sub n here is the leading coefficient, right? It's non-zero. And the rest part in the polynomial is a product of n linear polynomials in the form of x minus a constant. The constant could be real number, could be non-real complex numbers. So x minus c1, x minus c2, and so on, x minus cn. We can see c sub 1, c sub 2, and so on, all the way to c sub n. They are n zeros of the polynomial p of x. It's consistent with the content of the fundamental theorem of algebra. If the degree is n, then it has n zeros. The n zeros are c sub 1, c sub 2, all the way to c sub n. They don't have to be distinct, as I wrote here. C sub 1, c sub n are constants, possibly non-real complex constants, and not necessarily distinct. In other words, an nth degree polynomial can be factored as a product of n linear factors. Yeah, the two theorems actually tell us the same thing. If the polynomial function has degree n, then it has exactly n zeros. Then the function could be factored in this form. C sub 1, C sub 2, all the way to C sub n. They are the n zeros of the polynomial function p of x. They don't have to be distinct, and they don't have to be all real numbers. It could be non-real complex number. Okay? And the next theorem, try to interpret the linear factors theorem right above it. Let's see the content. The graph of an nth degree polynomial function has at most n x-intercepts and at most n-1 turning points. If we have a polynomial function with degree n, all the coefficients of the polynomial must be real numbers, of course. Then it has exactly n zeros, right? If the n zeros are all real numbers, then the function would have, if the n zeros are all real numbers and are all different, then the polynomial function would have exactly n x-intercepts. However, as we have mentioned earlier, the n zeros do not have to be all real, and the n zero do not have to be all distinct. So here the conclusion is, for any polynomial function with degree n, it has at most n x-intercepts, at most n x-intercepts. In that case, all the n zeros are real numbers. All the n zeros are different. If the polynomial with degree n has at most n x-intercepts, then of course it has at most n-1 turning points. What is a turning point? How do we define a turning point? I have the definition right here. Turning point is a point where the graph changes behavior from increasing to decreasing, or vice versa. I actually can show you the graph. Let's say this is a rectangular coordinate system. Let's use color red. Yeah, how about that? 1, 2, 3, 4. Okay. So how about we look at this graph? This graph corresponds to a polynomial function. And how many x-intercepts does this function have? X-intercepts. 1, let me use pink maybe. 1, 2, 3, 4, right? Yeah, this function has 4 x-intercepts. X-intercept is defined as intersection of the graph and the x-axis. X-axis is the horizontal scale. We can tell because the polynomial functions are all continuous. Then if the function cross the x-axis once, it's either going up or going down, right? Yeah. So let's say the graph crossed the first time. In order to time, here second time the graph crossed the x-axis. And the third time, the graph has to change the behavior from decreasing to increasing. Same thing here. In order for the graph to cross the fourth time, number 4, is the first, has to change the behavior. Let's see how many 4 to 3 is 4 minus 1 intercepts. Does that make sense? Yeah. So if a polynomial function, the graph of a polynomial function with degree n zeros, but those n zero function at p of x, for example, we have p of x k. That's okay. So if it's 0, then of course specificity. Let's say we have a 0, then the graph of the polynomial function would pass cross. The second case, if so on, we don't consider 0. We know 0 is also even, but we don't consider 0 here. At least the k has. So -2 is a 0 of the polynomial function with the multiple. Basically, those are the theorems we have seen. By the way, I have another 2 functions here, f of x and g of x. You can also use the graphing calculator to observe the number of x-intercepts, and the number of turning points. Yeah, so those 2 examples are for number of x-intercepts and the number of turning points for the polynomial function with degree n. All right, so let's see the first example. Sketch the graph of the function. Sketch the graph. The function is a polynomial function, of course, and the function is already factored. The function f equals the square of x times x minus 1. Anyone can tell me what's the degree of the polynomial function? You can pause and think. The answer is 3. Yeah, the function has degree 3. Actually, the leading term of the function is x to the power of third. You can find the graph for x cubed in your graphing calculator. You would know the function going up in quadrant 1 and going down in quadrant 3. Okay. So how many zeros this function is supposed to have if the degree is 3? By the fundamental theorem of algebra, if the degree is 3, then the function is supposed to have 3 zeros. The 3 zeros here are -4, -4, and 1. So you can see -4 here is a 0 with the multiplicity 2. Is that clear, everybody? Yeah, as I said here, I actually have the sentence written down right here. -4 is a 0 of the function with the multiplicity 2. 1 is a 0 of the function with the multiplicity 1. Then the graph of the function would cross through the x-axis at 1, 0, and touch and bounce back at -4, 0, because -4 has a multiplicity 2. 2 is even. Do you see what I'm saying? You can see the graph here. Turns out the green graph is the graph of the polynomial. This is a -2, -4 actually, I'm sorry. This is -4, and that is 1. Yeah, that is 1. This is a -4. It getting closer and touch and bounce back, because -4 is a 0 of multiplicity 2. 2 is even, and at 1 the function. So this is the vertical scale. Okay. Yeah, actually I can draw it here for you. So this is a -4, 0. This is 1, 0. As we see, as we have learned from the previous theorem, because -4 is a 0 with degree 2, is even, so the function gonna touch and bounce back. While at 1, 0, the function gonna cross through. Okay, so basically the graph is gonna look like this. Not very accurate, but it has all the important features. It going up in quadrant 1, going down in quadrant 3. Is that clear? You can use your graphing calculator to double check the result. Also, if you could find the y-intercept of the function, that could make your graph even better. Okay? Yeah. All right. So let's see another theorem here. Conjugate roots theorem. If we have a polynomial, this one, if we have a polynomial function with degree n, all the coefficients are real numbers. Suppose the function has a 0, a plus bi, when it has a minus bi as a 0 as well. You know what I'm saying here? In other words, if a polynomial function has a non-real complex number as a 0, then it must has is conjugate as 0 as well. Yeah, let me explain again. Make sure you understand this theorem. If we have a polynomial function, all the coefficients are real number, and we know a plus bi is a non-real complex 0, non-real complex 0. It must has like an even number of complex non-real complex zeros. Right? Is that clear? This is a pretty important theorem. We also have some problems designed to design for this problem. Okay, so let's see example 3 here. No, example 2 here. Let me copy example 2. All the notes are posted in Moodle. You know that, right? So let's see example 2 here. Let me write down the requirements. We need to factor a polynomial function p of x. P of x equals 2x to the power 4th plus 3x cubed minus 7x squared plus 8x plus 6. Yeah, let me double check. 2x to the power 4th plus 3x cubed minus 7x squared plus 8x plus 6. Yeah, we need to factor that polynomial completely. In C, anybody remember what is C? Complex number set. That fancy C represents complex number set. Given that, we have one more condition. Given that 1 plus I is a0. All right, let's see how do we solve this problem. Look at the function. Look at the polynomial function. What's the degree of the function? Degree of the function is 4, right? And the function is well written, is written in the standard form. You see leading term, degree 4, exponent 4, 3, 2, 1, 0, right? Yeah, it is in the standard form already. Then because the degree is 4, then the function should have 4 zeros, right? Yeah, so we are expecting to have 4 zeros for this function. Also, we know the function is supposed to be able to written as this form. Leading coefficient is 2, right? Leading coefficient are copied here. Leading coefficient and then x minus c1, x minus c2, x minus c3, x minus c4. Remember that theorem earlier? Because the function has a degree 4, then the function is supposed to be factored as leading coefficient and then times x minus c1, c2, x minus c2, x minus c3, x minus c4. c1, c2, c3, c4. What's the name of the theorem? Conjugate roots theorem. Let me write it down. By the conjugates roots theorem. Since 1 plus I is a 0, 1 minus I is also a 0. I'm going to use Q of x. So far so good? All right, so let's continue here. Give me 1 second. My surface like tend to crash once in a while. So we have 1 minus I here. And then we have a Q of x here. So I'm going to write 2 here. And I'm going to for you. And the result, write 2 here. And I'm going to for you. And the result of for you, I'm going to put it in the red parentheses. Okay? Yeah, you see, this is x is the first term. Negative parentheses 1 plus I is the second term. X is the first term. Negative parentheses 1 minus I is the second term. So we are going to for you here. For you here, so we have the first plus outside plus inside plus last times last. Okay. And x. Last, we have a negative 1 plus I here, right here, and we have negative 1 minus I here. Okay? Sorry about that. It's kind of like they all like put it too close together. So 2 here, and a bigger parenthesis in red, and the q of x right here. So x times x squared. And here, positive or negative, we have a negative 1 minus I x. Negative or positive, so we have a negative 1 plus I x. Negative or negative, so we have a positive. Positive 1 plus I times 1 minus I. Continue. Copy 2. If we divide both sides by this polynomial, we would have q of x. In other words, q of x is the quotient of p of x, which is 2x to the power 4th, 3x cubed minus 7x squared plus 8x plus 6, divided by 2x squared minus 4x plus 4. Division of two polynomials. What method we have learned for finding the quotient of two polynomials? By the way, the synthetic method doesn't apply here, okay? The divisor is not linear. Divisor is degree 2. So we have no choice. We're going to do, what is the method again? Long divisor. We have 3x squared minus 6x plus 6. And we subtract, we have 0, remainder. So we found the q of x here, right? This is q of x. This is q of x. Q of x is x squared plus 7 over 2x plus 3 over 2. And we don't like a fraction. You can factor half out. Then inside the parentheses, you should have 2x squared plus 7x plus divided by original leading coefficient. Right after you divide, you're going to simplify. And x plus 3 here. You see what I'm saying? So therefore, altogether, p of x can be written as 2. And x minus c1, c1 remember is 1 plus I. X minus c2, x minus 1 minus I. Multiply by half 2x plus 1, x plus 3. So that part is q of x. So the 2 and a half cancel each other. We actually end up with x minus 1 plus I. X minus 1 minus I. 2x plus 1. X plus 3. So that's how do we factor the given linear factors in the factorization. Alright? Is that clear to you? So by the way, what are the 4 zeros?